So this is part 2 of our chapter 3 review video. In part 1, we looked at how to set up some statements using some symbols and a couple of the different ways that statements can be true. And to be true, then both statements need to be true. For an or, one needs to be true, either one, but if they're both false, then it's false. And if and only if they have to match, so true, true, or false, false. That's how your overall statement is true. If-thens are the real interesting ones. Only true to false is false. True to true, false to true, and false to false. That overall combination, those will all be considered true for the overall statement. And so what we're going to do now is we're going to look at an if-then statement, and then we're going to set up some truth tables so that we get a little bit of practice with the truth tables, and then also see why this happens. So we're going to look at this statement. If Holly is playing with the toy, then Abby will want the same toy. And there's Holly and Abby. Abby is going to be 5, and Abby is going to be 3. And you can see them probably exhausted after playing with these two lifeless-looking toys. This used to be a rope in front of Holly, and this was some kind of weird giraffe duck-looking thing. Dog toys are really strange. We'll talk about Alice in a minute. So let's look at what's going on with our sentence here. If Holly is playing with a toy, we're going to make Holly is playing with a toy P. And we are going to make Abby will want the same toy Q. And we are dealing with a conditional because of the if-then. So in the middle goes our arrow. And so when we looked at the one with Abby going outside in the rain, it kind of felt like they were all saying the same thing. You go, well, how do you know what's true? How do you know what's not true? And we're going to talk about how to kind of compare those. And I had said it's a lot easier, actually, if you take the words and you make them symbols so that it doesn't kind of sway your opinion. If I were to take this original conditional and flop the order so that Q becomes my first and then my P becomes my second. Not that P becomes Q and Q becomes P. That's important to remember. You're not changing the variables. You're changing the order of which the variables show up. When you do that, then that's called the converse. So the converse changes the order so that this becomes if Q, then P. So if Abby wants the same toy, then Holly is playing with that toy. And sometimes when you change them from the symbols to the words, you kind of have to play with the grammar a little bit so it doesn't sound too crazy. And we say, well, that kind of sounds like saying the same thing. And that is what brings me to Alice. Alice in Wonderland was written by Lewis Carroll, but Lewis Carroll is a pen name for Charles Dodgson, and he was a mathematician, and he did a ton of work in logic and came up with a lot of rules that you'll look at in the later part of the chapter, which is why the book, if you ever read it, is really pretty crazy. And the Disney version of Alice is actually relatively close to what the book is, minus the creepy stuff, and there is a lot of creepy stuff in the book. But during the tea party, the Mad Hatter says to Alice, do you say what you mean, or do you mean what you say? And Alice says, well, they're the same thing. And he says, no, it's not. If that were the case, I breathe when I sleep would be the same as I sleep when I breathe. And then the dormouse, which is probably in here allegedly sleeping, pipes up and says, well, that's true for me. Of course, in the book, he is not sleeping, but for the kids, we say that's what's going on with him. And so what he's arguing is that the conditional and the converse of the conditional do not have the same truth value by the breathe when you sleep and sleep when you breathe statement. If you change the knots, and by knots I mean put in a knot or take out a knot, then that's the inverse. And the inverse keeps the same order but changes the signs, and I always kind of think of it inverse with signs, so I remember the I, right? No C in signs. And so that this becomes if not P, then not Q. So if Holly is not playing with the toy, then Abby will not want the same toy. And living in the same house with Holly and Abby, I can say I feel like that's saying the same thing. But we'll look at what the truth tables say. The most important one that you want to remember is the contrapositive. What the contrapositive does is both the inverse and the converse, swaps the order and swaps the signs. So it becomes not Q, then not P. So if Abby does not want the same toy, then Holly is not playing with that toy. And very much like Alice, we hear these and we say, gosh, they all kind of seem like the same exact thing. They all sound like they're the same true statement. So what we're going to do is find out which one actually is the exact same as the conditional. You would do that by using a truth table. So we're going to set up a truth table for the original, which is if P, then Q. And we're going to keep this part of the box the same for all of the other ones. The true, true, right? Because my first P could be true and then Q could be true, or P can be true and Q could be false. Maybe P is false and Q is true, and maybe P is false and Q is false. Those are the 4 different combinations that you can have if you're talking about 2 sentences. And if you're always talking about a P and a Q, these first 2 columns are always going to look the same. True, true, false, false, true, false, true, false. If P, then Q is our conditional. And if P, then Q is only false when true leads to false. That's the only time it's false. The rest of the time, it's true, right? Remember the car GPS scenario. If you're listening to it, then you don't get where you're going. That's not true. If you listen to it, you're going to get to where you're going. Or if you don't listen to it, you won't get to where you're going. And maybe if you screw up a couple of times and then you know a secret shortcut, you may get there also. This was kind of like the maybe situation, like you already know where you're going. But the only way that a conditional is false is if a true leads to a false. So we're going to take this answer column and we're going to compare this answer column to all the other answer columns and see which ones match. The one that matches exactly, that's the one that's the logical equivalent. So let's look at the converse now. Actually, I'm going to put it in a different color. So the converse, keeping the same setup here, P, Q, true, true, false, false, true, false, true, false. But now we're going from Q to P. So our one-way street has flipped directions. And so when you're reading it from your trues to your falses, you have to flip that direction this way too. Now you can't just put Q first and P second, because it would not be the exact same order that you have over here. So you don't want to change the order of the P's and the Q's in these first like ingredient columns, if you will. We're just going to read it backwards when we piece it together. A conditional is false when a true leads to a false. So this one right here, true leads to false. That's the only one that's going to be false. This is true to true, false to true, false to false. And so you can see right away, these are different. This is true, false, true, true. This is true, true, false, true. And these answer columns are not the same. So these are not the same statement. They don't have the same truth value. If P goes to Q, you cannot then assume that Q goes to P. Just because you can drive from north to south on a one-way street does not mean you can assume that you can drive from south to north, right? Because it could be a one-way street. Let's look at the inverse. The inverse, let's keep P and Q. We want those combinations to go in exactly the same way. Kind of like baking, right? The order that you add the ingredients changes up that chemical reaction. So it's important that you put it in the right way. But we need some nots here, right? Because the inverse says not P and not Q. That's another P. So not P, so not Q. And so we're going to need to talk about not P. And knots just flip the original column. So if it was true, now it's false. And same thing with Q. If it was true, it's now false. And if it was false, it's now true. So it's like a mirror image, right? Just kind of more like an inverter, right? Like if you do the contrast and if you're playing with like the iPad or something, you flop the colors. It's kind of like that. So now we can look at this. If I could squeeze it in. Kinda. There we go. And we're going to use these two columns. And we're going from P, the not P, to the not Q. False to false is true. False to true is true. True to false, that is false. True to true, that is true. And I got true, true, false, true. And that is not the same as this one. So he is not the logical equivalent either. So he's no good because these are different. And we're talking about back to this one. So he's a no, and he's a no. But notice that these two look awfully close to being the same thing, right? Kind of different makeup in here, right, because of the falses and the trues, but the same answer matrix. So let's look at the contrapositive. The contrapositive is going to add one more step onto this. And I'm going to go to the other, well, no, I'm going to scroll down so I have some room. Here's P. Here's Q. True, true, false, false, true, false, true, false. We need not P's, so let's flip the P column. We need a not Q, so let's flip the Q column. And now we're going for the contrapositive. You flip the order and the signs of the original. So we're going from Q, not Q, to here. So false to false, true. True to false, false. False to true, true. True to true, true. And lo and behold, they are the same, even though you can't see it. Let's see if I can go out a little bit. So now it's a little too small, but you can see that this is the same as that. True, false, true, 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 false, true, true. Holly didn't like that apparently. And so that means that those two are actually saying the same exact thing. So what this means to you and what this will mean for the rest of this chapter is that the conditional and the contrapositive are the logical equivalents of one another. So that if P not Q, if you have that, then you know that this is saying the exact same thing. These guys are the logical equivalents. And so when you're given a bunch of statements and you want to try to piece together what's going on, what's true and what's not true, you can use the contrapositive to rewrite conditionals. You can use De Morgan's law to rewrite ands and ors. And then there's some other conditionals that you can kind of piece together to make the conjunction, and a couple of ones that you can pull apart to do a disjunction. But those are the two big ones, the contrapositive and the De Morgan's law. Those are the ones that you use the most. The other thing that was way up in the beginning part of this is something called Euler's diagrams. Now, Euler's diagrams, it looks like it's spelled Euler, but it's Euler, kind of use circles. And some of them will sound pretty silly when you're looking at the textbook, but if you try to remove things that you think are true, then it will make a lot more sense. Let me get you an example. This is number 4 on 3-6, and it says you make an Euler diagram to see whether or not this syllogism is valid or invalid. Is this argument a valid argument? These three little dots right here mean therefore. So this is your first premise, this is your second premise, and this is your conclusion. And you're going to use the laws, this detachment, law of syllogism, what the heck are the other ones called? They all have different names. Like there used to be called modus tollens, but I think we call it something else now. But there's all these different rules in 3.5 that you look at to use this. But you can also use some circles. Some lizards are poisonous. So in the world of things that are poisonous, some of those things are lizards. Yes, the Venn diagrams are back, right? So some, right in here, lizards are poisonous. So here's the world of the lizards that are poisonous. A skink, whatever that is, I don't know if that's real, but apparently it's a lizard. So a skink, I don't know if I'm even saying that right, allegedly is a lizard. Can I then make the conclusion a skink is poisonous? No. This is invalid. You don't know if it's poison. I know it's a lizard, but if I was going to go put this lovely little skink thingy in here, I don't know if I'm putting the skink into the, oops. Well, I'll just do this. I don't know if I'm taking skink and I'm saying, oh, you go right in here and then not poisonous, or do you go in here? It didn't say. It didn't say if whether or not this was like all skinks are poisonous, all lizards are poisonous, or something like that. I just know it's a lizard. I don't know what kind. Now, if it said the skink is poisonous, and this guy is a lizard, I couldn't make that either, because it would just be the same thing on the other side. Well, I know is a skink here, or is it in here? That's also a lizard, because there's lots of things that are poisonous. Spiders, I can't think of anything else, but there's lots of stuff that is also poisonous. So what you can do is kind of draw those Venn diagrams and use that to kind of help you out. The one big thing you want to remember is the opposite of all is not none. The opposite is some. So, and the opposite of none is not all. That's also a some. So some are not, and some are. Because if I say, all of my students are math majors, I don't need every one of you to say that you're not a math major to prove me wrong. I just need one person. And so this is all of the stuff from chapter 3. If you want to see anything else, let me know. And hopefully this helped a little bit.